Ladies, gentlemen, organizers. So I thank you very much for inviting me. I'd like to talk about this joint work with my student, Pablo Azar, and I'd like to reclaim where it belongs to a theoretical computer scientist and the cryptography in particular, the Turing legacy for the work on proofs. And today we're going to talk about rational proofs. Before we dive in, I'd like to know by any chance if there are anybody in the audience who is not a computer scientist. Everybody is, or everybody's afraid to say. Very good. So therefore, I define nothing and assume everything. So speaking of proofs, so what are classical proofs? So these are very old constructs, right? They go back 2,500 years. That is from our ancient Greece. By the way, Nigel, you see what happens when we have no Google access and Google Images is failing? And so, and then he proceeded and essentially impeded, and he got formalized later by Gödel, by Turing, but essentially is the same source, right? So strings, proofs are strings with spatial syntactic properties. They are syntactic objects, right? You have a bunch of axioms, you have a bunch of inference rules, and you say, well, I write down a proof is a sequence of line. Any line can be an axiom, or if I write A and A implies B, then I can write B on a single line, and if I write the end of the statement on a single line, that's the proof is correct. Thank you very much. So then, if these are proofs, what are efficient classical proofs? Elementary, Watson. So these are, if proofs are syntactic strings, these are strings, and have to be short, so that, and they have to be easy to verify. And that's what MP is, right? Short, easy to verify strings, as defined by Cook and Levin in the early 90s. But what there is a problem is that, already NP is a little bit a tight jacket, right? You don't not too comfortable in it, because there are all kinds of things like co-MP. What if you want to prove that a formula is not satisfiable? You don't know what to do with an MP. What if you want to prove how many satisfying assignments a formula has? Well, good luck. What if blah, 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 you want to go until P space, right? So NP doesn't really, so either we live in a world in which there are no proofs for things we'd love to prove, or we change the notion of proofs. And of course, given the choice, we would like to change our habits rather than being in darkness. So later on in the 80s, we've joined to work with Shafi and Rakov, and independently by Moran. So we say, no, forget proofs. These are not syntactic objects, these are processes. And so these are processes, essentially exchanges between a prover and a verifier. Think of them like machines, Turing machines. And that satisfies a completeness axiom, which essentially means you can prove anything which is true, and a soundness axiom, anything false you cannot convince the verifier, except with a small probability that you can pump out, right, arbitrarily low. Very good. So then what are efficient proofs? Now becomes something else. So essentially are these pairs of proving and verifying machine? Well, the verifying machine is efficient. Efficient means time is efficient, polynomial time, and therefore communication is efficient, polynomial number of rounds. All right. And it took a while, but after a while now we know that actually P space, representative of a lot of things we would like to prove, are actually indeed in IP. Excellent. So, in the formalization of a proof, you need a PR firm. Computer science is too high because P space with kind of classes, right? They're terrible. And so interactive proof systems didn't work very much, but Arthur Merlin games, even though equivalent, are much more colorful. So I like it. And so here are our heroes, Arthur on the left and Merlin on the right. And the question is, what is a string in a language L, yes or no? And you know, because you declared yourself theoretical computer science, how it goes. In this interaction, Merlin sends a string, and Arthur just volunteers a random string, just flips coins. String, coins, string, coins, string, coins. And at the end, they get up their proofs, and so proofs after proofs, so they discovered how to do this, so they lived happily ever after. By proving a theorem a day keeps the doctor away. Until few centuries later, says, how about you prove this theorem? This is minors may be around, we don't translate this. What the hell happened? What happens, Dumbledore got hired by Goldman Sachs, Gandalf by Citi, Potter by JP Morgan, and Merlin says, who am I? So now I have the money in my mind. I'm not going to help you to prove your stupid theorem. Thanks very much. I have better things to do. all right, Arthur is a reasonable man. He understands that now has to pay, and he will pay. So the question that now, which I'm investigating today, is that how do you pay a math expert? The answer is no matter what, a lot, but let's put it on the side. But what is the preferred method? Then of course, there is the fixed price model. You get the $1 for a correct proof and $0 if you're again convinced, right? But what we really want to investigate, if we are going to, can we have a better use of monetary incentives to prove more theorems and actually to prove them faster? And actually, when we say faster, I really mean fast. And when we measure efficiency here, I propose to really focus on the number of rounds. Because you and I, even I, which I'm technologically challenged as anybody, has exchanged a few megabytes with somebody, right? And I've done, even not me, but my laptop has done a few millions of operations, right? But whenever you, at least not I, has engaged in a million or a few mega rounds of interaction, never, right? So even an SSL is a few sessions, so that's very, very, very quick. So what we want to do, is there a better way to essentially pay for theorems that can let us do things which you cannot do before? Welcome to the world of rational Merlin and Arthur. RMA, what does it mean? That now Merlin is rational. Forget what everybody knows, that there are good guys and bad guys. There are only selfish guys, there are rational guys who want to maximize their own utility, okay? And Merlin, unfortunately, has become one of them. So let me tell you what does it mean in this world to prove that a language L belongs to the class rational Merlin-Arthur with k rounds of interaction. That means that there are two subjects now, an output of function, pi, that is a polynomial time. So essentially is at the end of the predicate, you accept or reject or whatever you think about that way. And a reward function, R, green R, the color of money, that is also polynomial time, okay? So this output, the function pi and the function R are common knowledge. They are up in the sky, Arthur sees them, Merlin sees them, right? So they know what we're talking about. And then when they engage, it says, how about proving whether X is an L, says Arthur. No problem. Strings, coins, random strings at the end, k rounds, because this is I want to define what does it mean to belong to RMA K. And then at the end, there is going to be a transcript, right? Starts with the input X, followed by whatever Merlin said, whatever Arthur said, Merlin said, outside, until the end. Now we have a transcript. Very good. What are the rules of the game? Once we generated the transcript together, then R of this transcript, X I added just for emphasis because it's already part of the transcript, is given in cash to Merlin. Okay? That's the money Merlin gets. And then it says, well, now Merlin has been paid, where is the theorem? Simple. Now, you apply the function pi, the output function, on the transcript, and you get an output. And that's what Arthur believes at the end. Is this clear? Oh, no, I think I want to focus on the yes instances for now, but you should see it'll disappear anyway. Okay? So these are the rules of the game. The predicate, pardon? If it is a language, yes, the output is binary, right? We can do the same for functions, but for now it's languages, right? So you interact, he gets paid the amount that R specifies, and Arthur believes whatever the output function evaluated on the transcript tells him to. Okay? How about verification? No verification. We don't verify anything. We pay, we believe. We pay, we believe. We pay, we believe. Okay? That's easy. So, well, that is the thing. Assume you are Merlin, and you see here pi. What do you care about pi? Nothing. That's what Arthur is going to output. That's his business. Let him fend for himself. But you care about R. So if you were Merlin, what would you do? Well, you try to develop the transcript, right? So Arthur here is a nice guy, tosses coins. Otherwise, we can actually do a coin flip protocols. I mean, there is enough cryptographers to, to do that here, right? But so you choose whatever you have to say in order to generate a transcript, we call it T star, that maximizes the expected reward, right? That's what you want to do. That's what a rational Merlin is going to do. And so what you have to make sure is that he's going to get this in cache, and when he does so, for the same T star that maximizes utility, your pi is going to give you the truth. Okay? So now we set it as a game. I know that you are rational, which means you are selfish and try to maximize your utility. And without knowing anything about membership in this language, because I'm a poor Arthur, right, a polynomial time bounded, I'm going to choose carefully this pi and this r, which are both polynomial time, because, by the way, if I'm going to pay, I must figure out how much money I owe you. So r has to be polynomial time. Pi better be polynomial time, because that's the only thing I can do to evaluate. But I must strike this great balance so that when I know that you're going to maximize your utility, I get the truth out of you. Is this clear? So what we are going to do here, for this all to work, we have to strike a delicate balance between we must devise this pi and r, which has to be simple, and yet somehow do the job, right? That's the juggling act. Good. So I want to prove that doing things in this manner actually gives, reasonable efficiencies. And the first thing I want to prove that Sharpie, which is a non-trivial language, right, is MP, co-MP, Sharpie. We can actually get it, of course, is in Merlin Arthur, right, in IP, but that is polynomial time. So the real question is, can we do it in quadratic time? Can we do it in linear time? Can you do it in polylogarithmic number of rounds? So what's your guess? Constant. Ooh, some optimist. Let's be optimistic, but one round, okay? I want to prove that you can do this in one round. And before we do this, I want to make a remark that is, by the way, notice that Sharpie is not even in MA, right? In MA, no matter how many rounds, right? Otherwise, the polynomial time hierarchy collapses. And I never cared about this hierarchy, but now I do, because I have my own hierarchy, and so I started caring. Okay, so here's what we want to do. Because I mentioned the word theorem, and there is going to be proofs. The proofs are going to be rational, but this is the last rational proof I'm going to give you. Now I want to be paid from now on. And so this is going to be an old-fashioned proof, and it's going to need all kinds of usual traps of a proof. First, I have to define formally what this RMA is. Then I want to recall what Sharpie is, and then I want to prove a theorem. Okay. Here is RMA1. Right. The question is, what is f of x? Because Sharpie is function much more than languages, so I'm shifting towards the function. There is an x and an f as an input, and the king wants to know what the value f of x is. And Merlin tells you why, the truth. And the king tosses coins, and he gets cash, and he believes pi of y, whatever that means. Okay? That's what we have to do, because there is very little room to maneuver in one round, right? That's what happens. Okay, so Merlin, I remind you, he will choose the y that maximizes his reward, and it better be that of this y, pi of y star is going to be f of x. Okay? That's what I want to prove. Just good. So formally, I think says, I'm going to say it 3 times, hoping that after that you are on your own. I'm not going to repeat more than this. So there is a function now, because I don't want to tie myself in knots and define this for languages. There is a function from strings to strings that belongs to RMA1 if there exists a polynomial p, and there is a randomized polynomial time function r, a polynomial time function pi, such that there exists a unique y star maximizing the expectation, and pi y star is equal to f of x. Okay. Now, yes?
Why do you
because we came here first. It's like Christopher Columbus, who wasn't there first, but he put the flag there and he decided, now this belongs to the King of Spain. Somebody else lived there, never mind. So, you know, so we have a choice. We don't really need it, but, you know, you can get some extra elegance if you say it's unique.
You need it, Silvio. If you don't have it, Merlin can return anything he wants and maximize his money without Arthur getting anything.
No, then you must be careful that if there is multiple, then the pi, you know, you must agree on everything, right? So I want to say, but it's an extra additional lines of reasoning. I want to dismiss it and let me define for simplicity that is unique. Yeah? Okay. Now let me give you a proof sketch. Okay, how am I going to prove it? Mind you, there is some reduction to do, but you know, we can focus, I think I'm going to believe it on this, just on the CNF formula. I want to prove it, you know, how many satisfying instances a CNF formula has, right? So phi is our formula. Now, the king asks, how many satisfying assignments? Trivialities for our magicians. 2 to the 301 plus 17. That's every, you know, he knows that for sure. The only question is, how does he convince of this? That's a lot to prove. And if you, one way to prove it is to say, listen, if you take this machine M, but in general for Sharpie, you have a machine M, you would say, how many Y's can I have a machine accept? There is going to be exponential many things. So you cannot go on by on and send 2 to the 301 of them. Let's recall that 2 to the 300 exceeds the number of electrons in the universe. So that's a lot. Okay, so there are no one-round proofs so far. No matter, not an LMP, not an IP, nothing like this. Good. So that's why we ask for external help. And to whom? To economics. Economics? I mean, you sure mean that we are going to go the rescue of economics? No, I actually mean that way, okay? And it may look surprising, but I think that we have helped economics a lot as theoretical computer scientists in the last decade, and now we are going to get some returns. Good. Why is economics helpful at all? Because there are certain things which are really human values, and everybody thinks about them, including the economist. Am I on tape? Too late. So, actually, the economists have thought of this a lot, because there is a world of asymmetry of information, right? So very often we have one player who has more information than the other, and the other guy wants to acquire this information. So, but what is information? Now, and how do we guarantee that it's correct, right? That's the whole question. Now, in computation, information is the output of a hard-to-compute function f, and the correctness is guaranteed by a proof. And in fact, you know, I think the whole essence of zero knowledge is really that, because this is what zero knowledge proof is about. Because you know, you say if I'm not going to compute at all, anything that is polynomial time is devoid of information. Anything which is not polynomial time, then you start getting interesting, right? So that is really for computer science what is information. It's the output of a long computation. In economics, instead, information is knowledge of a distribution over what? Over some set of states S, called the states of the world, and correctness comes from incentives. So now this community, not unlike ours, has been thinking for 50 long years about, or even more, in fact, our asymmetry of information too. So it's not by chance that if the concept is fundamental, different communities are going to intersect. So how do we incentivize this correctness in economics? And the answer is by proper scoring rule. And this is a technique which is developed in the 50s. In fact, actually 1950 on the nose, the first one. So it's over 60 years old by now. So let me tell you what they are. So what is a scoring rule? So remember, there is a set of omega, which is the set of the states of the world, and is a mapping from distribution over omega times omega into the reals. And you can think of it like a two-stage game, one player against nature. You know, what is nature? Nature is a distribution over the state of the world. That's what nature is, right? So that nature is this D, this distribution here. So in stage one, the player chooses a distribution P, in stage 2, nature draws a state little omega according to the distribution D, because that's the nature distribution, and the player receives the payoff S of PW. Remember, that's the scoring rule. Okay, so therefore, you immediately see that the player's expected utility is the expectation over omega drawn from D of the scoring rule applied to P, whatever you said, and omega, whatever state has been drawn. And the scoring rule is strictly proper if for any distribution P different from nature, when you sample according to nature, this score is always greater than this other score. You must admit that this is a very elegant, simple idea. Right? It's all the hallmarks of a great idea. It's fundamental, it's simple, and promises to be useful. It does accept one defect, at least to me, that I don't even know what it means and what has to do with the game at hand. So let me try to reinterpret this in our thing. What is the scoring rule here? So let's just assume that omega is a bunch, there is going to be the Champions League. Unfortunately, Milan has been just eliminated, but I drove the slides before. And so there are all these team 1, team 2, right, etc., etc. And the king wants to know, really, Merlin knows the distribution, who is going to win the Champions League. The one who does not know is the king. The king would like to know, maybe because he wants to sit next to the, where the coach of the winning team is going to be. Maybe he wants to be photographed with the winning team, whatever kingly things do. So there is this distribution, but only he doesn't know. Who does? Merlin does. And Merlin knows that the probability that AC Milan wins is P1 because it's team number 1. The probability of Manchester United is P2, and so on and so forth. So Arthur says, tell me, Merlin, what D is, please. And Merlin, in this game, can say anything. He's going to say a distribution Q. Good. After it tells Q, hey, guess what? Somebody is going to win the championship. So nature is going to draw the winner from the true distribution D. Never mind what Merlin says. Nature doesn't listen to Merlin. Does whatever nature does best, right? He follows his own rule and he follows in sample according to his own distribution. Very good. Then the king takes a bunch of money determined by what Merlin said, the distribution he volunteered, and the really output, who the winner was, and ships it to Merlin. Good. Okay, that's the game. So let's just assume the nature selected Milan. Then that's the money the Merlin ships. Notice that the money depends on who actually, not only depends on S, but it can shrink and grow according to whatever Q is and whatever the winner is. And if it would have been Manchester United, it would have been a different sum of money, and so on and so forth. Okay, now if you are Merlin now, and you say, well, in this game, now that I explain again the game, right, that's the second round, and in particular close to our application, what did you do? What is your expected thing if you say W, expected payoff if you say W? Well, is the probability that Milan wins times the reward you get if Milan wins, plus the probability that Manchester United wins times the probability of this score that depends on Manchester United winning and you are sending Q and so on and so forth, right? That is expected value. So what, of course, Merlin is going to do is going to choose the Q that maximizes this return. And what is a scoring rule? A scoring rule is this magical S such that the way to maximize this is to say the truth. So if you really know the distribution of nature, and the best thing to do is to say that, because this maximizes your reward. Okay? Excellent. Now, there is only one thing left to do, is to say, well, this is a great definition. I see how to plug in the contest at the end, not exactly quite, but look close. There is money transacting, there is truth which are distributional. These are not computer science theorems, right? And information not in the computer science sense, but in the economic sense, says where are these scoring rules? Here is one, and is a very popular one, and is due to Mr. Good in his Good scoring rule, which is, look how simple, really elementary in this construction, is the logarithm of d applied to w. Okay, so somebody tells you the distribution d, really w is selected by nature. You say, according to this distribution d, what value probability you give to w? You say number x, take the log of it, and that's the money you have to pay. All right. There is, however, a problem here, and actually two. The first thing, the scoring rule is unbounded, and the second one is actually negative. In fact, the logarithm that remember is unbounded is actually negative. What does this mean in our contest? That you see, Arthur pays the money. This money is unbounded, can be a lot, and moreover, is negative. So is Merlin who has to pay Arthur. So it doesn't quite work, right? So nobody, no true Merlin or expert will be motivated by having to pay this unbounded amount of money. Good.
In this case, it is bounded.
Pardon?
In the case of the Sharpie, it is bounded. I mean, let's say the probability of being a satisfying
well, but is negative, right? Which is a problem. So, right. So, in fact, here is the other Breyer scoring rule, which is this one. And this has the big advantage always of being truthful, again, and bounded, okay? And in fact, it is bounded between -2 and 0. I don't like -2 and 0. This is negative anyway. So why don't we add something, another 2 right there, and now it's between 0 and 2. So rather than paying $1 a theorem, now you're going to pay a variable amount between $0 and $2, right? Depending, that's the plan. There is, however, a catch here that this distribution here, right, is hard to encode, right? Because to give a distribution is to specify what the distribution is at every point a state of the world. Good luck. Then S can be hard to compute. This doesn't promise anything good. For any element in the support, you have to some of these things. And the setting is going to be different because I want to know something about the theorem, where is the distribution, and so on and so forth. Good. Let us instead convince ourselves that these are not too far apart, okay? Remember where we are. There is a formula phi. That's the number of satisfying assignment. And we are going to reduce one word to another in 6 easy steps. Step number 1. Step number 1 is, if Merlin knows this magic number, he can always divide by 2 to the n. Remember, it's an n variable formula. There are so n variables. And so, in fact, it's a one-to-one correspondence. So if he knows this number, you might as well bet he knows y. And why don't we put this in his mind instead? Because that's a one-to-one. It's an easy transformation. Second of all, let me define now the following probability over 0, 1. In fact, if there is a distribution of 0, 1, that is an easy distribution because I have to specify at 2 values. And actually, if I'm smart, I only need to specify at 1 value. And without a loss of generality, let's specify at 1. Okay? D of 1 is the probability that if you choose a random assignment of the variables, the formula is satisfied. Right? That exists, this probability. Nobody can take away from me or from you or anybody. Good. Then I'm going to say that notice that according to this distribution, D of 1 is exactly the y in Merlin's. Right? Because this is the number of satisfying assignment divided by 2 to the n, this is D of 1. Therefore, this y actually is an encoding of D. So in general, to encode a distribution, good luck. But here is going to be an n-bit number, right? That's easy. Second or third, I'm going to claim that Merlin knows how to sample this distribution D. Are you kidding me? Of course he knows. Because what is going to stop, Arthur knows how to sample. What is going to stop Arthur, me, you, or anyone to randomly assign the variables, the true, false of a variable, and see what happens to the formula, right? Nobody. And Arthur wants to incentivize Merlin to reveal D, says, gee, then all of a sudden, Arthur can sample D, Merlin knows D, Arthur wants to incentivize. What do you have to do? we had to do Breyer's scoring rule, which in general looks horrible, but here, because it's over 0, 1, and things are so encoded, this is actually a piece of cake. Okay? So what is going to happen is that Arthur says this many instances. It's going to say 2 to 301 plus 17, right? That is divided 2 to the n. That's what it does. Merlin is going to toss coins and see a bit b, 0, 1, depending whether a formula after a random assignment is satisfied or not. And is going to return this amount of money. And notice that this norm here is just y square, right? That's no easy deal. The end. Very easy. QD. Okay, so that is called theorem 0. Okay, that's a good start. So sharp P is in one round RMA. And first of all, because I'm not using and encrypting anything in this talk, but if you manage to decode what I say hat off, so hopefully we've done well so far, even though invested in a general different model, I want you to pause and notice that in this model, which I grant you is not our usual model, but this proof is zero knowledge. Because why? What was the whole elaboration about zero knowledge, right? To say, oh, the proof of a theorem reveals more than the statement of a theorem. Here, the proof coincides with the statement. You don't know actually what the statement is. You don't know what the truth is. If you say y, you cannot reveal more than y. I think information theoretically is a perfect zero knowledge proof. I claim it's a quintessential CS proof also. I mean, when I thought about the CS proofs, I thought really the application of really compensating somebody for doing a lot of work, right? I want to say, I don't know how to compute f, but she knows how to compute f. So here is my x, tell me f of x. And then you say, well, but now I don't want to pay a fixed amount at the time, right? $1 per theorem. But you say, now I want to say, but I need the evidence that you're giving me the correct y. Otherwise, why should I pay? And a CS proof was giving you what? This short certificate of correctness. My certificate is even shorter because there is no certificate, right? I tell you f, x, you tell me y, I'm done, right? And then I give you, compensate you accordingly. So if we want to compensate an f, this is actually a perfect CS proof also. Comes for free. Okay, that's as much as we can milk out of this theorem 0. Time to move on. Let me tell you about theorem 1. And theorem 1 essentially says, well, now that we know that RMA 1 includes sharp P, how much does it include? And so let me put these bounds here. This is a P to the sharp 1P. What the hell does sharp 1P is? This means that is a polynomial time machine that makes one call and one call only to a sharp P oracle. And in fact, let me prove it to you. How I'm going to prove? By imitating the machine. So I'm a polynomial time. I will do a polynomial time walk. All of a sudden I stop. I must make one query, which is a sharp P query. But I already told you how to do a sharp query. I make one query to Merlin that I know how to reward for him. He gives back the answer. When I continue walk, etc. Done. End of the proof. The other side of the proof is more interesting. First of all, because actually it represents for us that there are things money can't buy. So that means if you are above this thing, right, then there's so much that you can do. You can pay somebody for, right? You cannot pay and get away with it if you are outside of this class, okay? So therefore, let me give you a sketch where this is proof. And the sketch is easy. This is not what the hardness is. Okay, so recall what RMA1 is, right? And then now I want to recall for a language. Now I go backwards, right? Not function, but languages. Why? Because NP to the sharp P is a complexity for languages. And so there is a polynomial, the randomized reward function, the outcome function pi, such this, blah, blah, blah. We have seen this already. Only we need to do that if a language has this really incentive-based program, then it belongs to NP to the sharp P. So therefore, let me prove that in NP to the sharp P, we can find the magical y star that maximizes Merlin rewards, because that's what Merlin is going to say, and therefore it better be foundable in NP to the sharp p. Good. So let me define this auxiliary function, f of y, which is the expected reward, right? And let me actually notice only one thing, that remember that R is probabilistic, right? So X is the input, Merlin tells you Y, he's going to get what? In expectation, R of xy, the expectation of R plus y. But notice that there are only 2 to the polynomially many possible values, because there are so many y's that you can say. And then this function, I claim to be postponed the proof, can actually be computed in p to the sharp p for any fixed y. Okay, let's put it aside. If this is true, then in non-deterministically, I can actually find the y star that maximizes it. And after I find it, well, evaluating pi, right, on x and y star, that is a piece of cake, because pi it was polynomial time, and therefore I know that whether x is not. So barring these 3 question marks, essentially we have proven that L can be decided in NP to the sharp p. So, but why should f of y be computable in p to the sharp p? That is a QED if and only if you can settle this. This is also very easy. So let g of x be any randomized polynomial time function. Then, so I want to show something a bit more general, that if I take the expectation, I take a random r, and I take the expectation over r of gxr, can be computed in p to the sharp p. And the reason this is so is the following. Give it a name to g to the xr, call it z. Okay? Then zi is the ith bit of z. And then I claim that it suffices to compute the expectation of g over x, it suffices to compute the expectation of z of I. Why? The linearity of expectation. Because my z is going to be the sum of z1 times the coefficient, which is 2 to the 0. z2 times 2 to the 2, right? So if I know this, I'm done. All right. And therefore, now that you want to compute the expectation of zi, what is this? Well, mi is a randomized polynomial time machine, right, that computes zi, and the expectation of zi is really proportional to the number of paths, accepting paths of a machine, and this can be computed in one sharp p query. But because now I have n bits, it's not anymore a single call to the sharp p oracle, but there's to be n calls, but that's exactly as many calls we do, and we are done. And therefore, we can put back the QED in the previous slide where it belonged. Okay? Done. So, okay. So far, that's what we have actually proven. And I want to notice, however, that the rational Merlin Arthur with one round is more powerful than MA. And that's something to do with Mr. Toda, because Mr. Toda proved that P to the one query to sharp P includes already the polynomial time hierarchy, and if MA belongs to the polynomial time, right, otherwise is more powerful than Merlin Arthur unless the polynomial time hierarchy collapses. Okay. Now let me ask a question. What happens if we have more rounds? Now we have a pretty good grasp of what we can do in one round. So next, we want to look at the rounds. What happens where we have 2 rounds, 3 rounds? Where does this thing fit? Right? Good. To say this, let me tell you something about which I knew nothing about it until not long ago, which is the counting hierarchy. But it's a beautiful concept, so let me tell you what it is. The counting hierarchy, CP1 equal PP. If you are rusty as I am about PP, what is PP? PP is you want to think in a non-deterministic machines, right? You want to find if the number of accepting paths is greater than the number of rejecting paths, right? So you have here your oracle tapes, you fill it in. For every content of the oracle, now you have an accepted or rejected. You want to know if there are more ones than zeros. So that's PP. And that is CP1. CP2 is PP to the, with a counting one oracle, also known as PP to the PP. And essentially means that after you get over here, you have to call a PP oracle to know if you're accepting or not. And similarly, CPK is recursively defined this way. And this hierarchy has been defined by Wagner and Toran. Okay? And what is the theorem? And this I'm not going to prove. Okay? And the theorem is that actually rational Merlin R2 with k rounds is nicely sandwiched between CPK and CPK plus 1. So there is some slackness there, but it really gives you roughly a very good characterization of what these rational proofs can do, right? Has something to do really with the counting hierarchy. So I didn't care before about the counting hierarchy, I do now. But let me tell you a little bit, I'm not going to go into any proof details of this. Let me tell you essentially what the idea is, and that is something that for sure Shafi and hopefully somebody else here is going to like. And that is because we are going to reduce, to prove this theorem, we are going to prove an intermediate theorem first. We introduce an auxiliary class only for the proof. It's going to disappear, which is R m to the k a, which means a rational proof with k distinct Merlins. You remember what k distinct Merlins is? Essentially provers who don't interact with each other, right? And in fact, you already know that two provers who don't interact with each other, then it gives, next, right? So here, the Merlins, they don't interact with each other. You pay them separately, that's okay. That is easy to work with. Because you want to say, what you want to maximize is only one piece, heaven knows what happens. The trick is to fold all these k Merlins into the same person. Because now, you see, I'm not going to, if I'm Merlin, I'm not going to say truthfully answer your question to receive the maximum amount of money now, because maybe I have more money to make later if I lie consistently. And it's easy to lie consistently if I am the same Merlin, right? So I have to be careful of how to set up a reward system so that even though you're dealing with the same person, I oblige him to say truth, 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 truth all the time. And that is his best course of strategy. So there is some work to do, and it's not going to be our job today. Done. Good. So let me tell you that if you've not discovered already, that this is a theoretical work, right? And in fact, right, so theory for the sake of theory. And before you raise a hand and you ask a nasty question, let me take some wind out of your nasty sail and say, of course, we have to, this Merlin, we have to assume that he's going to care about exponentially small sense, right? But this is necessarily so, right? Because either that or Arthur has to pay exponential amount of money, which he doesn't have anyway. Do we agree? So that is really theory, but we are undeterred. Why? Because we are theoreticians, and we know that theorem actually eventually leads to practice. But how is not so clear yet. So first of all, at this point, having done this, I'm in the sweet spot of every talk, in which the speaker, as a reward for his own talking so much, is allowed to say in conclusions anything he wants. So I'm going to I have a captive audience, and I'm going to say. The first thing is autolimbing. What is autolimbing? That to go out on a limb, which I'm doing now, and which means does the counting hierarchy collapse? So this hierarchy, we don't know. So see, before, I bet that people would say, I don't think it collapses because I don't believe this collapses, and therefore by reduction, so to speak, I don't believe this collapses either. But now, unfortunately, we have now a fear because this is also, there is another analogy between the two things. And these guys collapse. So that is totally unclear to what is going to happen to this hierarchy. That is my autolimbing expedition. What is next? Next is extending. Okay, extending, by the way, what? Up or down? Down. Why not up? Because you can actually prove, because these things are probability over polynomial time machines, right? You cannot prove more than p space, no matter how many rounds of interaction you're going to have. But I'm doing things for very high-level muscle provers who can do sharp p things, right? How about very limited Merlins? And to still, given their both presence, a good language, I really want to have rational proofs for muggles, okay? Which is this nice notion that have Goldwasser and Rothblum, Schaffing guy here. And I think actually their techniques most probably are going to apply, and we want to push down these things. And I'll tell you later why I think I want to push them down. But first of all, now about in terms of summarizing, we have a new complexity class, which is this RMA. We have short rational proofs for sharp p, which we care about. And even though I didn't care about, now we have a constant round rational proofs for the counting hierarchy. And how about unifying? So that is also another conclusion, because essentially we can see that the world is not so diverse, because humans are humans, they care about the same things. Research community is a research community made by humans who care about the same thing. So asymmetrical information is a common human concern, and so these two approaches actually naturally blend together. How to reward an expert, how to trust an expert. So they are in principle different things, but turns out they're not so different. And in particular, there is a very interesting parallelism between scoring rules and interactive proofs. And if you want to unify even more, let's now over-unify. And what is this Harmonia Mundi? So Harmonia Mundi is, despite all the traps of modernity that I claim for myself, I'm a medieval, at most, Renaissance man. So this is this essentially mystical, if you want, concept. There is a basic unity between the mind, the universe, and God. And to study one is to study the other. For your information, I do believe in it, okay? That's my problem, actually my source of inspiration too. So what does this to do? How about bio? See why I want to push it forward? Because this, an organism works, right? This is, I'm fantasizing now, right? I earn my right, so I say anything I want. So remember, in order for an organism as complex as ours, or even as nail, something less complex than ours, to work, you really have to gather a lot of information from the periphery to get organized decision and continue living, right? Whether it's a macrophage who presents to you some piece of a virus, right? So I think at the end there ought to be a system of reward. Reward is not going to be in cash. Maybe I'm going to secrete something that you like, some hormone or whatever it is, right? That is, and so therefore I don't have incentive to lie, and you get enough information about a system like this. So we have to push this down, because computing these rewards, how much they get in response to what is presented to you, has to be very simple, but it has to be really truthful in this scoring rule sense, in this rational type of proof. Shorter. How about E? What is E? Is energy, right? So because a reward, remember, what is it? Is a function which goes into the reals. The reals can model a lot of things. So we consider the real cache, something Shafi hates, because everything I do now in game theory doesn't do cache, she doesn't pay attention. She's not interested in cache, good for her. But for the rest of us, maybe different story. But he could actually be for energy. Because what I do that I know about physics, and I'm going to show that now, is that very physical systems, they want to minimize energy. Right? So if you want to maximize a reward, or minimizing a reward is the same thing. And if the reward is not cash, but is energy, there can be some connection over there between things that are actually truthful and they go the right way, because you are up to try to minimizing something. And finally, let me say that we should always be cognizant that the best question is the one we don't know how to ask yet. Thank you. Coffee? Oh. Yeah.
I asked for the question.
So maybe I'll go back to your nasty question and ask, because you seem to hint, so do you know actually that if we restrict ourselves to polynomial payments or constant payments and polynomial maximum, everything collapses to the interactive proofs, or can you do more even in this setting? Or do you not know that?
I'm say I do not know the answer completely, but I think that things are not going to collapse, and in fact, I think that your work is going to be crucial to leverage these things because it seems to be priced right, and in fact, it may be as so simple as to do a reinterpretation, right, of your work, but that needs to be done. I think is doable. How much? If you go to constants, then I don't know. Right? Yep.
So Silvia, I guess also possibly a nasty question, but probably there is a simple answer. So you looked rationalizing the prover, but not the verifier to some extent. So for example, for this class the one class RMA1, for example, the verifier, presumably if he kind of cares about paying like the less money, for example, he can probably
right.
There should be some kind of simple answer. Or,
Right. So, well, guys, there may be some simple answer, but we are in new territory, right? So that's why I said, I was very happy to work in the Merlin Arthur because Merlin is honest and only knows how to do is to. So if you have an oracle or random oracle or even a random beacon, you don't need a random oracle here, it just gives you on the clock a bunch of random bits that you can do. If you can do now if you can do it now as a coin flip, I was trying to sneak it in. We could do it as a coin flip, but and maybe this works, but it's also not so clear that it works, right? But now speaking about, I suspect that maybe the coin flip is going to work, or doing a cryptographically coin flip. But in principle, I think that this opens the door to much more ambitious question in cryptography. Because remember, cryptography, as well as proofs, is the quintessential realm where good and evil interact. And how about reinterpreting our basic cryptographic primitives? Is there, for instance, such a thing like a rational commitment? I want to be evocative, I don't know, over rational anything. In which you say, yes, I could somehow decode in two ways, right? Decommit in two ways, but somehow if I want to maximize the money, then I better stick to what I originally put in the box. We don't know. It's another world out there, but certainly if anybody can figure out, we are, right? Yes.
I have two questions. Maybe the first one is the same as Guy asked. It seems to me that the taking this expectation, which sounds very innocent, is actually not innocent at all. If I give somebody the choice to get $1 million with probability 1 minus something very small, or $1 zillion with probability very, very small, they would probably pick 1 million, because that zillion wouldn't mean much anyway. So, but if you took a strategy that maximizes expectation, they would choose the zillion.
Well,
I mean, they would choose the option.
So I must say, so we have to start from somewhere. By the way, because of these days I'm paying more attention to mechanism design and game theory, I try to reinterpret mechanism design with much weaker rationality than before. Right? So for instance, typically if you ask an economist, if you say, what is rationality? Is expectation maximizers. That's what should be rational. But you and I know that this is not true. Because if I really, at least for me, it's not true. Because if somebody gives me the following gamble, with probability 100% of the time, he give me $10 billion. Or, with probability 51%, he gives me $20 billion, and the probability half, he gives me 0. And he says, here is the $10 billion check in my hand, and here is a coin, should I toss it? I grab the $10 billion and run to the Caribbean as fast as I can. And I consider myself reasonably rational. So when you have to work actually into lower rationality in mechanism design, obliges us to work harder. Because now we have to allocate and allow more room for variability among rational players. And that takes more math to handle. But here I'm happy, that's hopefully the beginning of something, to take whatever the economists dish out, right, without any much thought, but you're right, that there is room here for exploring more robust ways, but my prediction is it's going to be harder to prove too, because fair is fair, right?
My second question is that the reward function capital R is probabilistic, and Arthur pays that amount, so he has to flip coins to select a value that he would
Right. I think I have to decide which one. If the guy flips coins, there is no probabilism in R, right? So I have to be careful. I think I may actually start the slides in one way and unnecessarily so, right? Because once there is Arthur, the only reason for Arthur to flip coins is that I wanted to have this in expectation, right? So R could be deterministic, and Arthur flips coins, and that's what I meant, right? Yep.
In your model, Merlin receives a reward only at the end of the interactions. It's conceivable to have a setting where after each round of interaction, Merlin gets some reward, and it's trying to maximize the total expectation of the rewards, and that brings it closer.
Right. That's what I was saying. In fact, that's actually what conceptually we do when we want to prove what happens in RMA K with K rounds. Because any time that essentially, yes, that we face it this way. The answer is yes. That you have to be careful. In fact, that's what I was saying before. You have to be careful. So if you pay at the end or at the beginning, but it doesn't matter too much. My guess is that you can allow. See, the trick is to at least if you are in control of R, right? So if you are in control of R, what you can do is to say that you get most of your reward now, and I'm going to discount the reward you're going to do it later. But I'm going to discount it so much that when you start in your rational to say, hey, the best thing I want to do is I answer truthfully this question, because no matter what money I'm going to make later is going to be so much discounted that I better say truth. So in principle it could happen. I'm not sure it's going to be very crucial.
Then quick synthetic question. I mean, you define RMA instead of RAM. Usually kind of people, I don't know why, but people like AM more as a prover goes last. Have you looked as a...
Well, that necessarily is, at least in my case, is MA, because if I flip the coins first, and now you're in round one, and now you say, why? No, I have no control over you anymore, right? So the only reason that I can do it in one round is that I'm going to buy as a leak trick or sleight of hands, I'm going to say, you go first, I go last, and then and it's here that I can prove that you better say truthfully why, because I'm going to toss coins later. But if all coins already been tossed, then there is no expectation, then the guy can really trick me.
Well, for one round, but let's say for two, I mean, it's clear that RMA 1 belongs to RAM 1, right? Belongs to RMA 2 and so on.
Right,
but
at the end of the day, I suspect that this is going to be, well, that's a conjecture. Prove me wrong, I'm not going to be mad at you. But I suspect that if it really is essential, the last thing of Merlin, then there is enough slackness at the end. Maybe not, maybe whatever I will say. If it is essential, he really wants to carve another little reward. And then if there are no coin tosses, I think that even in milli sense, it's going to be hard to control this. And I think that the last one to talk, my suspicion is going to be Merlin, even in a multi-round setting.
So this is my point about Arthur lying in
right. I think that it is correctly ordered, but certainly it's true for one round. I suspect it's also to be true for multi-round. Yeah, but I don't know. Yep.
If you looked on the quantum version of RMA, does it tell you anything new about CMA or BTP? How does it stack together?
No, I haven't. The only thing that I've actually considered, without really thinking about it, is whether this can actually provide another avenue for quantum algorithms, quantum computing. Because, again, if you go back to the minimizing energy type of thing, maybe you can set up the variables, right? And then you say, okay, now go to the minimum state, and then it's going to give you the result of the computation. So I can see that there is potentially something could be done there, not by me, because I know nothing about quantum mechanics. I cannot exploit it, and I have no immediate plans to learn it, to try to see if there is. But so that is the only thing I ask, at least impossible. So that for me is an open question. And the other thing that you say is that to say, well, it's a slightly different question. In fact, a very different question to say that if you put now quantum computing, you bake it in from the very beginning, where things change. I have no idea. Well, thanks again.